Thank you for the introduction, and thank you for the invitation for me to join this very meaningful Science for the Public initiative. So today my talk is Understanding Motion Through Language of the Dance, AI in Motion Science and Performing Arts. Okay, so before we start, I want to ask you a question. For the audiences here, how many of you have tried ChatGPT? If you have, can you raise your hands? Okay, so not all of you, but I think at least 30%. So, since today we are talking about language of the dance, so let's start with language first. We know that ChatGPT is a language tool, right? Let's ask ChatGPT. All right, so, hi ChatGPT, who are you? So let's see what it will give us as a response. Right, so, hello, I am ChatGPT, a language model developed by OpenAI. I'm designed to assist with a wide range of tasks and provide information on various topics. And you can think of me as a computer program capable of generating human and text based on the prompts I receive. And how can I assist you today? Let's continue to ask. All right, so today, since our topic is creative arts, right? Let's ask, how can a machine create art? So this is a philosophical, very fundamental question for all the artists as well as the scientists, the AI researchers today. So let's see how ChatGPT, as an AI product itself, how it thinks about the answer to this question. All right, so how can machines create art? And ChatGPT gives us a long answer to generalize into these several points. These are the possibilities. The first step is randomization. So machines can program to generate random patterns, shapes, or colors, and resulting in unique and unpredictable answers. And these are the wonderful things of art. Second, data visualization. Machine can analyze and interpret data sets, such as weather patterns. We know that this is a Hong Kong observatory, right? So the beauty also lies in the pattern of how the rainstorms, the clouds moves, right? And such as the stock market data, social media trends, and translate them into visual representations. And third one, machine learning. We know that machine learning is just an algorithm to learn on existing data and then try to create by exploring through the learned patterns. And last one, so the next one is interactive art, right? AI can help you to interact with algorithms and give you some surprising results, and also augmentation and collaboration, all right? So these are some of the choices ChatGPT think that how machine can create art. And now let's see some of the two examples. Right? They are from two very different eras, but they represent to us how machine art generation is about in different era. The first one is called Oscillon 40. It is created by an artist called Ben Lapolsky. It is one of the first pieces recorded of art created by a computer, and Lapolsky used an oscilloscope to manipulate and photograph electronic waves, and they're displayed on a fluorescent screen. All right, so this piece of work is actually following the pattern of art creation just suggested by ChatGPT. And what are the steps? There are randomization. We know that the electrons are generated randomly. All right, and then some physics and algorithms applied. In here is the voltage that we applied, which will affect the flying trajectory of the electrons that will finally hit on the fluorescent screen. And then the screen is a sort of data visualization tool provided to us. All right, so although this is art creation, we can say that it follows patterns and procedures. And then second one, this is actually a very famous one. I just wonder, how many of you in the audience have seen this picture before? If you have, please raise your hand. All right, so two in the front. I guess you work in AI, so you know about this picture. All right, so this is famous because this picture is created purely by AI. And it is famous not just because of that, because it actually won a painting competition among all real human artists. It won the first place in the digital category at the Colorado State Fair. Okay, so this painting is called Theatre de l'Opéra Spatial, drawn by Jason Alien. right? So there's a lot of reports about this because it caused a lot of controversial, because this is an AI-generated picture, right? And the artists are not happy. And the author says, I won and I didn't break any rules. That's it. Okay, so although we know that the way this image is generated as compared to Oscillon 40 is drastically different, right? The technology involved is also different, but they follow the same pattern. Also, randomization, physics, and data visualization. But there are also differences. What are differences? Randomization is reflected in how we use random seeds as input to AI models, right? And instead of relying on physics and algorithms, right? Here the artists use prompt engineering. It tests and use different text, right, to encourage the AI to generate an image as wonderful as this one. And then finally, how we visualize the data. And now we are not using a screen anymore. We are using actually a visual decoder, right? It decodes information in the latent space into the pixel space. So this decoder has to be trained over large quantities of data. So that's the connection. All right, so let's continue to ask ChatGPT again, right? Since we say the last one, it is created by text prompts, right? Obviously, text becomes a very important part of modern AI for art. So let's ask ChatGPT again, how is text and how is language models helping us to create images? All right? This is ChatGPT's answer. There are a lot of words that are difficult to explain if you don't have scientific background, but generally they're saying they can convert given text descriptions into images. They can automatically add annotation and descriptions to images, providing information about the image. And also, they can guide the process of image generation by providing textual prompts. So this describes the whole process. Okay? And now, that's the examples. Let's see and dive a little bit deeper, right? And let's see why language is going to be helpful, and this is going to be a vital role to be played for creative arts, right? And let's begin from the very start. What is a language? Okay, so language, according to Wikipedia, is a structured system of communication that consists of grammar and vocabulary. It is primary means by which human conveys meaning in spoken, written, and other forms. And according to ChatGPT, there are between 6,000 and 7,000 languages spoken globally. So there are a lot of them. All right, and also today, we will be looking at how the language's role is playing in the era of AIGC, especially for motion. AIGC stands for Artificial Intelligence for Generative Contents. Okay, so what forms a language, right? The most basic questions we have to answer are listed as the following. The first is, how do we choose to represent words? Words are most basic and fundamental atoms of a language, right? And then the second one is, how do we design the grammar and algorithm so that the words can be connected together? Different combinations can be leading to drastically different expressions of meaning, right? So these two aspects is important for what is a language. Okay, so before we go deeper, right, let's first see how we convey meanings as human as compared to computers. Let's start with an example. If we human want to describe the weather, we usually use a sentence like this. For example, the temperature is 30 degrees Celsius. The high is 30 degrees, sorry, and the low is 26. The wind is 13 miles per hour, right? 25 millimeters of rain, relative humidity is 33%, right? So long sentence, very verbal, right? Very reader friendly. But this is how humans record or express information. For computer, this information will be sorted and recorded as a string or a list of numbers like this: 30, 26, 13, 25, and 0.83. All right? They look to you just like a meaningless list of numbers, but computer, they will have their own protocols. They have predefined format to interpret what this means, right? And this string of numbers are called vectors, and they are the most fundamental way of how computers will record and understand information. Another example is when we want to say, what day is it today, right? For example, today is Saturday. Right? How can computer express that information? So they have listed all possible days: Sunday, Monday, Tuesday, until Saturday, right? So for the wrong answers, they give it a 0. For the right answer, they just give it a 1. All right? So to express what day is it today, for computer, they might use a format of this: 0, 0, 0 at some place that corresponds to the day today is 1, and all the other places are all zeros, right? So this is how computer express the date. And this way of registration of information is called one-hot encoding. Okay, so one-hot encoding is actually one of the most conventional way human record and archive information, right? Think about how we organize the words in a dictionary. They are ordered according to their alphabetical orders, right? First, starting with the first letter, second letter, and etc., etc. As long as you have a letter or you have a word, right, its location in the dictionary will be uniquely identified. And second example is how our librarians label the books. They have their own Dewey Decimal System, which can help us to identify what subject, right, what number of the book it is. It gives every book a unique number that will help you, right, to find them very quickly according to what you want in the computer system. Okay? However, this conventional way of registering and recording information actually stand in the way of AI. And today we are going to talk about, in the age of AI, actually the biggest change is happening at the most fundamental way of how we identify and express a word in a dictionary. So for a computer, we use word embedding. Okay? So just like how we express the weather today, we're no longer using a one-hot number to express information, but instead we use a string of numbers. Okay? So that a lot more information can be packed together as compared to one-hot encoding, right? And the word can be clustered around each other when their semantic meaning are close to each other, right? We can not only use vectors to represent a word, we can also use it to represent a sentence. Okay, so that the semantic meaning, semantic neighbors around it, right, will tell us the context, right? What's in front and what is after this word can also be embedded into this sentence. All right, so why this word embedding, vector embedding concept is important? Let's look at it from two very obvious examples. For one-code embedding, we know that we represent a word using a sparse vector with only one non-zero element, right? So there's no semantic correlation between the words. For example, there are two words, cats and dog. They will have ones at different locations of the vector. Okay, so we have another pair of words, cat and computer. Their differences are the same with cat and dog. But according to our knowledge, we know that cat and dog are much similar to each other, right? They are both four-legged mammals. As compared with cat and computer, they are much more different as compared to cat and dog pair. Right? But one-hot encoding cannot tell us this information of the relationship between words. Right? So a consequence that this brings to us is that in order for us to understand a new word, we have to record and learn everything in front. We cannot know when you give us a new meaning of a word, we don't know its meaning, right? So this is the conventional way. But what can word embedding bring us, right? So for word embedding, we know that we represent the word using a dense and low-dimensional vectors, so that words with similar semantics are more closer to each other in the space, which will improve the generalization property of the representation. And now another example. For example, if we have a sentence like this, cat is eating fish in the kitchen, right? And if our training or model have seen this sentence before, and because the sentence embedding, right, can be quite flexible and more manipulable in the word embedding space, so that when we see a different sentence like this, dog eats meat in the bedroom, okay? So due to the fact that we already know cat and dog are similar concepts, kitchen and bedroom, meat and fish are similar concepts. So it is highly likely that the model will believe dog eats meat in the bedroom is a sentence that makes sense, that tells us something, it's relevant. Okay, so this is the advantage that word embedding can bring us as compared to the conventional way that we register information. Okay, and also this is actually the fundamental format representation for large language model or language models. All right, and now we just talked with ChatGPT. ChatGPT is also a language model. It is a large language model, right? So what is a language model? A language model contains a dictionary, all right? Like cats, dog, machine, language, etc., etc. Each word will have a vector to represent its meaning. And then, given this dictionary, we will be able to model the probability of a certain arrangement of words is an actual sensible sentence, right? So for the words, you cannot just randomly pick some and then concatenate them together and you think this is a word that has meaning. No, right? A language model will try to figure out what kind of combination makes sense. For example, if we give you a sentence to the language model, these dancers are quite amazing. So this has a very high probability. The language model will tell you this is a good sentence. All right? So if you give a sequence of words like ballet, fast jump, great food, then obviously the language model will be able to identify, all right, these are not meaningful expression. Okay, so this is just simple examples, but all language models are just trained on this combination of prediction of probability of arrangement is true or not to be a real sentence. Okay, and it is trained on large amounts of data, and it learns from the true sentences that they are true, right? And then maybe from the bad sentences that they are bad, right? And they learn this through simple games, like filling the missing words, right? Complete the whole sentence, etc., etc. And large language models just go through extremely large amounts of sentences and words over books and in the library, and over the sentences over the internet. And after this long periods of learning, they will gain the natural language expertise and the sort of artificial intelligence, just like ChatGPT. Okay, so ChatGPT, in its core, is simple, right? It tells you, okay, are you telling me a sentence? I will give you a probability. You give me a sentence, and then I will give you this probability, what will be the next highest word that will be having the highest possibility to be actually the next. Okay? All right. So with large language models, we can do a lot of downstream tasks, and they include language translation, question and answering, essay writing, content summary, and chat box, etc., etc. Right? And the recent boom in language models, especially in the appearing of ChatGPT, can be credited to the learning of an extremely large language model, right? Which looks into almost all available texts and sentences on the internet. All right. I'm not sure if you have heard the concept of transformer. Right? So actually, this is one of the cornerstone of the recent large language model development. You can think about it and understand it as a mechanism that enables the language models to look into longer sentences and remember them so that the predictions are more relevant. Okay, so compared with normal language models, which is in no means a very new concept, why is ChatGPT, right, so popular right now? So on top of a normal language model, right, it involves a concept called human feedback. So it learns over large quantities of data, and they employ human experts to tell you whether the current prediction is good or not, so that the model can be fine-tuned and give you this sort of human-like conversation feeling. Okay, so that's about language model, right? Now let's go to its application in AIGC. Actually, language models have been used very extensively in generative arts, especially recently, right? And how language model is helping us to generate images. And now let's look at this example. So say we have a large data set, and they contain a large amount of images. And each image is paired with a text as description. For example, we have an image here as a puppy, and its corresponding text will be the image, the Aussie puppy, right? So you can, the sentence can be really descriptive and it can be really simple, right? And then we want the model to understand how these language descriptions and language elements are connected to the pixels in the image. And how this connection is built is also a simple game, actually. So we give them a vector label, both for the text and also the image pair, and make sure, right, that their label values get closer to each other if they are paired. And if they are not, we try to use our algorithm to make them further apart. Okay? And after rounds of iterations and optimization, we will have a model that can accurately discern the subtle differences in text descriptions and how this should be reflected in the painting details, and how the differences in the painting should be reflected and described in words. For example, we have this restyle transformer, right? If we have, say, we have an input image of Taylor Swift, and we use words to guide it into different styles, we can see the style, the generation will be very good, very amazing, right? And here we have another column, 2 rows of example, right? So we have the image of Barack Obama. If we input the text, Mohawk hairstyle, it can change the hairstyle of Obama into this hippie look, right? And we say we input an image of Taylor Swift again and input the prompt without makeup. Okay, so this is what this generative model thinks. Okay, so if we have the image of a cat and we input cute cat, the language model, right, will know that a larger eye will make a cat cuter, so that it will lead to the regeneration of image of pixels to make the cat having a new look. All right, so this is actually output from an image generation model called Stable Diffusion, right? So what it does is that it tries to learn the connection between image and text in the latent space and use a so-called diffusion model, right, to gradually guide the newly generated image pixels, right, to make sure that the generation direction, which is an iterative process, is strongly coupled with the text guidance, right? So this is actually one of the most recent technologies that is generating a lot of amazing effects and creates products such as Midjourney, right? So we can see an example. This is a text-based image generation interface, right? We can say, we can input a text here, such as a cat, right? And then it will automatically generate this image for you, which is a cat, right? And then we can further add more adjectives, right? A tabby cat, so it's a cat with striped patterns. And then this cat will have a new look, like this. And we can further add more descriptions. A tabby cat with a Christmas hat. Okay? As we become more descriptive, we know that the details that we require in the image will also be more specific, right? So this image generation is guided by the text, and the image generator or the visual decoder is understanding what we want it to do. We can also use it for video generation. All right, so video generation is similar to image generation in the sense that we generate the keyframes, and then making it like a video, we have to make sure that the frames are transited, are interpolated smoothly. All right, so this transition is not done in the pixel space, but in the hidden space, so that we can see that the semantic and the transition will be more natural. Okay, for example, here we enter 3 text prompts as the 3 keyframes. The first one is a cat, and then an owl, and then a tiger. Cat, owl, and tiger. All right? And then let's generate. We will see this outcome. Cat, it will be deformed into an owl, right? And then into a tiger. And the transition is extremely smooth, because it's guided by the interpolated vectors in the hidden space. Okay, so this is what text can do for image generation. Okay, so why this is helping in image generation? So this text is given to you from a scientific point of view, right? Several keywords, semantically meaningful, continuous word embedding space, right? And visual encoders learn passively from the supervision containing the vast amount of data on the internet and redistribute visual embedding space, blah, blah, blah. These are scientific words, right? But you don't need to understand them. What you need to understand is there are a lot of text available over the internet. Tons of them, and they are easy to get, they are free to get, and we have large resources to train on them to give us a large language model. But there are not so many images, right? Although we have a lot, but compared to the huge amount of text that exists there, is actually a very, very small amount of image data. So what we need to do, or what we are doing here, is actually just we learn a large language model first, and then try to associate it and let it guide the subtle details of image and generation of other modalities of arts, right? So we use text, some sort of text, as a guidance or as a teacher for other generations of signals, right? So this is not just restricted for images. We can also use it to generate music, right? So this is an output from Music LM developed by Google. We can use a string of text to generate a sequence of music notes using the same idea or ideology of music image generation. Let's see, right? So we first give a sentence of description. The main soundtrack of an arcade game, so it's a game music, all right? It is fast-paced and upbeat with a catchy electronic guitar stuff. The music is repetitive and easy to remember, but with unexpected sounds, the crystal crashes or drum rolls. All right, very, very verbal, very descriptive. And let's see what the Music LM interpret this segment of sentences. Okay, so I am not a music expert. I can't read all these meanings in the music myself, all right? But maybe some of you are more professional than me, all right? You can just go to their Music LM. It's free of use, right? You can try some of your text and see if the The model is expressing the music notes according to your desire, right? So I'm not going to play all the examples that I have here, but another example I'm going to give you is that you can also control the generation of music precise to the seconds. It means I generate a piece of music and I specify at what part of the music I want what style, and then I want them to be consistent, transition along the whole piece. For example, here we have a music. In the beginning, it says time to meditate. Okay, and now it's time to wake up. Wake up. And now, time to run. Alright, so I guess this music must be trained over Indian music because you can taste the style, right? So what I want to say is that language model is really powerful, right? It can give you visual descriptions, but it can also give you text and time indicators to precisely control this music. Right, so this is what text can bring us in music and in visual art generation. Sorry, I need to stop this. I don't know why I Ooh, sorry. Okay, so now let's come to the topic today. How we can use text to generate motion and generate dance. Okay, so our thinking is that we want to use some sort of text language to help us program motion. All right, and we want to use so-called choreographers or dancers' own language to program, just like computer programmers use Python. And we want to ask whether it is possible that we develop a foundation model that will help us to automatically generate a new choreography, just like ChatGPT would write an essay for us. Okay? And we know that there is actually a language for dancers and choreographers, and this is called Laban notation. So Laban notation is actually an annotation system. In a way, it is very similar to music notes. Right? We know that music notes runs horizontally, right? And different stuff, different bars represent the pitch, right? But as contrary, Laban notation runs from bottom up. It starts from the bottom and runs up. And the columns here, the staff here, does not represent pitch. It represents the usage of different body parts. For example, in the center, we have body support, and then we have leg, and we have body, and we have arm, etc., etc. Okay? And then Laban notation use the shape to indicate direction, and use shading to indicate the level of each movement. And we have example here. This is an example of Laban notation movement, right? So according to the place of the symbols are put, right? These two columns represent the use of hands. And the black means the hand is put down, right? And then the shape means hand reaching forward, and then to the side and back again. So put two hands together, it's like this. So this is actually a very classical ballet arm movement. Okay, so this is how Laban notation describes motion. Actually, this is not a very new language. It's introduced in the 1840s by a German-Hungarian kinematographer called Rudolf Laban. Right? So it was widely used by kinematographers and choreographers in the past. But nowadays, for students, dancers in the performing schools, they like to use video because obviously it's more obvious and straightforward, right? But witnessing how language models right, can help us to generate all those amazing pieces of art. We believe, and after discussion with choreographers, professional dancers in the performing arts schools, we believe this language system will have huge potential, right, in creating and generating natural dances for us automatically. Okay, so for the Laban notation, they actually have their own language system. They have their own words, like the use of different body parts, right? Different actions names, right? They have their own verbs, actions. They have their own adverbs to describe duration, timing, etc., etc. And this all aligns very well with our natural language system. Okay, so this will encourage us to develop motion GPT. All right, so this is what we are doing in our lab. We are developing a language model for motion. Of course, this is not going to be as complex and as a large language model, just like ChatGPT, because the vocabulary and the grammar will be much simpler, and we cannot afford to train a ChatGPT ourselves anyway, okay? But still, we are developing this foundation model to help us excavate the rich context that's embedded in the cross-modality backgrounds when a dancer is dancing. For example, we can use the text, right? Usually we have a description, we have a synopsis to describe a piece of music. We can use the video and images, right, to encourage and inspire the dancer how to dance. And we also have the music, of course, and we also have physiological signals, both from the choreographers and also from the audiences, to tell us what is expected, what is the artistic interpretation that is most efficient at this specific moment. Okay, so given this context, the motion GPT, just like ChatGPT, will automatically help us to write out a piece of Laban notation. And this Laban notation will be decoded by a decoder, just like visual decoder, right, into trajectories of the dancers. Okay, so in order to do that, we are actually collaborating with performing arts schools to create one of the world's largest annotated data set that connects Laban notation and accurate 3D joint trajectories. Okay, so this is actually an example, visual example of the data capture process that we have. So given the Laban notation on the left, our dancers is dancing, right, and doing actions according to the script. And the actual 3D trajectories are recorded here. And this is a motion capture system, actually. We can see that there are markers sticked on the joints of the performers. And we have infrared light cameras, which will detect the location, 3D location of these markers, and interpret the structure of the skeleton of the dancers. All right, so this is a Laban visualizer developed by us, right, which we can directly decode Laban notation into actual human trajectories. And we can archive the trajectories into Laban notation code. Okay, so these are the tools development. And another very interesting application of language of the dance is that it can help us to understand and distinguish the dancing styles. So let us look at this example. We have two dancers here, a boy and a girl, right? The boy is a typical classical ballet dancer, and the girl is a traditional Chinese dancer. They are dancing actually according to the same piece of Laban notation, but with very different styles. Right? So we have another piece of music on the right, which you can obviously see the connection of motion element, but also the differences in their styles. Okay, so this is a very useful tool. Right? So this is another piece of motion that we generated using text sky. So this is a piece of dance that is mimicking the motion of a jellyfish at the background. I'm not sure if you can see the connection. Okay, so is another example. We're connecting the visual clues of the sea waves, right, and use it to trigger the generation of motion. You see how the whirlpool, the direction of the change of the water direction is driving, right, how the dancers correspond dance. All right, I think that's all of my presentation. Thank you.